So, ladies and gentlemen, we are now ready to launch into our MSCA 2020.HR conference. We have an amazing program ahead of us. And before we introduce our keynote speaker, I'd like to give a couple of remarks to you as a moderator, to you, our participants. First of all, who is with us today? We have a total of 645 registered participants from 57 countries around the world. So of course we are primarily from Europe. However, we have 70 participants from Latin America, North America, Asia, Australia. So welcome to all of you, really for joining us from around the world for this conference. Interestingly, also mentioned by Commissioner Gabriel about the importance of intersectoral cooperation in research, and interestingly, with regards to our participants, 60% of you today are from the academic sector, but also we have 27% of participants from government or public institutions, and 13% from other non-academic institutions, so from the private sector and non-profit sector. So we have a diverse crowd, which again shows the importance of research to all different sectors of our society. So regarding your role today, ladies and gentlemen, we obviously have a range of interesting panel discussions, but we want to hear what you think about this. So during each panel discussion, you will all have the opportunity to ask questions via the platform, and we really invite you to ask as many difficult questions for our speakers. So really send us all your questions via the platform, and we will try and incorporate as many of those as we can into the Q&A session with the panelists. Another very important aspect that we'd like to emphasize in this conference is that we have 8 MSCA finalists for the MSCA awards. And this means that who decides who will win these awards? You do. So we would invite you to go and check out the MSCA finalists projects, which are featured in the expo booths you have on the platform, and to cast your votes for the projects that you think are most inspiring in each of the 3 categories that we'll be presenting a bit later today. So I think, ladies and gentlemen, we are now ready to begin. And what better way to begin a conference on mobility and brain circulation than to hear firsthand how mobility has impacted the academic career and scientific achievements of a young researcher. So it's now my pleasure to introduce our keynote speaker today. Our keynote speaker is Dr. Vibor Jelić, who is an astrophysicist from the Ruđer Bošković Institute here in Zagreb, in Croatia, where he works as the head of the laboratory for astroparticle physics and astrophysics. He graduated from the science faculty of the University of Zagreb, and he obtained both his PhD and a postdoctoral training in the Netherlands at the University of Groningen. His areas of research are experimental cosmology and radio astronomy, and he's been actively involved in radio telescope scientific projects. And together with an international team of scientists, he traced for radiation about 13 billion years old from the period of the formation of the first stars in space. He has published over 50 papers in international academic journals and has given over 50 lectures at international scientific conferences. So Dr. Jelić, welcome to our conference, and we are all looking forward to your keynote speech entitled Benefits and Challenges of Mobility in Research, Personal Experience of an Astrophysicist. So Dr. Jelić, the floor is yours.
Hello everyone, and thank you to the organizers for giving me opportunity to give some personal experience as an astrophysicist to say a few words about the benefits and challenges of the mobility in research. So while I was preparing this presentation, I was thinking what's the best way to do this. So I decided basically to present the path of my career, what I learned throughout my career on the importance of mobility, but also what were the challenges that I had during this path. And in order to make this presentation a bit more interesting, and actually why we are doing all of this is, of course, an excellent science, I also decided to add a few slides about a very beautiful project that I'm involved in and that could not be done without mobility in research across the whole Europe. So for me, the mobility in my career, it all started in 2006. So actually, after I graduated at University of Zagreb, I said goodbye to my friends, and I moved to University City of Groningen in the Netherlands, where actually I started my PhD, and unexpectedly I stayed there for 10 years before I moved back to Zagreb. At University of Groningen, I joined an excellent team of international and Dutch researchers that were organized in the LOFAR Epoch of Reionization Key Science Project, which basically had the aim with the novel and the new telescope, the low frequency array, that you will hear a bit later about it, decided to search for the first stars in the universe. So in order to understand how difficult this task is and what was the main aim of this project, I would like just give a short history of the universe. So we know that the universe began with a Big Bang around 13.8 billion years ago, and basically at the beginning the universe was extremely small, and since the Big Bang up to today the universe is expanding. And while the universe expands, basically its temperature is lowering down, and this is the main and the most crucial process which allows a structure formation in the universe. For my specific project, the first important epoch that happened in the history in the universe happened around 380,000 years after the Big Bang, so-called the recombination, when the electrons and protons combined to a neutral hydrogen atoms, and basically the universe became neutral. The photons, so basically the light from that period, could now suddenly easily travel around and across the universe, and actually today we can make and detect this old and faint radiation and learned about the beginnings of the universe. But after the neutral hydrogen atoms were formed, the gravity is becoming the dominant force in the universe, and basically this is the beginning of serious structure formation and evolution in the universe. And it took quite some time for the first structures to form in the universe. So between 200 million years up to 1 billion years after the Big Bang, the first stars and the first galaxies started to form in the universe, but also their light started to destroy, to ionize the surrounding intergalactic medium, mostly neutral hydrogen atoms, and this period when the universe went from a transition of being neutral to being again ionized, we call the epoch of reionization. The problem today is that we only know and we only have a certain constraints on the epoch of reionization, but we really don't know all the details. We also don't know what were the properties of the first stars and first galaxies in the universe. So for the last few decades, there are a few theoretical efforts and later on experimental efforts to try to directly probe this epoch and try to find the answers about the first stars in the universe. So the way to do it, because we are basically want to probe how the neutral hydrogen atoms went from neutral to ionized state, the best way to do it is actually to try to measure the amount of neutral hydrogen atoms through cosmic history. And one way to do it is to use a famous 21 centimeter line of a neutral hydrogen atom. So basically the neutral hydrogen atom consists of a proton and of electron, and they can have a quantum state, so-called the spin, in parallel and anti-parallel state. And when we go from a parallel to anti-parallel state, where parallel state has a slightly higher energy than anti-parallel state, due to conservation of energy, we have emission of a photon which has a wavelength of 21 centimeter. But because this emission was emitted 1 billion years ago, due to expansion of the universe, the wavelength of this emitted photon will be stretched, and today it will have a wavelength between 1.5 and 2.5 meters. So if we want to convert this into the frequencies, basically this corresponds to the frequencies between 100 and 200 megahertz roughly, which is the same frequency range where we all listen to the radio stations. So in order to detect this ancient and very faint cosmological signal that will tell us how the first stars in the universe affected the surrounding intergalactic medium, we need a radio telescope. And currently we have several low-frequency arrays, or better to say radio telescopes, that are able to probe this faint and cosmological emission. One project is a true European project, and it's called the LOFAR, the Low Frequency Radio Array Telescope, which has the most of the stations in the Netherlands, but today we have stations spread almost across the whole Europe. The second project is a Murchison Wildfield Array, which is a combined project between Australian partners and Americans. And then in a near future, we will have even a larger telescope, which is called a Square Kilometre Array, which is currently under construction in South Africa and Australia. And actually, by looking all these amazing telescopes, which all have a goal, but not only to probe the cosmic history, actually we can see that such large instruments, it's almost impossible to make if we have research done only in one country and if we don't have ability to enhance mobility between these countries. So now I will say a few words about the LOFAR telescope, because actually my career started with the LOFAR telescope, and I was heavily involved in enrollment of the LOFAR telescope. So the LOFAR telescope is the low frequency array, which consists of two types of antennas: high band antennas, which are sensitive to radio waves between 100 and 250 megahertz, and the low band antennas, which are sensitive to the radio emission between 10 and 80 megahertz. And as you can see on the images, these high band and low band antennas are very simple in their construction. These are basically the most simplest dipole antennas, which are stick to the ground, and they are able to detect emission from all sides from the sky. So now it's the question why this telescope was only built today. And the reason is that in the LOFAR telescope we have today more than 10,000 these dipole antennas spread across the whole Europe, and in a real time they all observe the same parts of the sky and allow scientists to do science. So here is a short video which basically shows a fly over the central part of the LOFAR telescope, where we can see the highest concentration of high band antennas and low band antennas that we use to do science in radio astronomy. But also it's interesting that in order to get funds to build such a large telescope, the network of these detectors was used to put also not only the detectors to do the radio astronomy, but also to do the geophysics and agronomy, because basically you have a network and high-speed internet spread across one large area, and then it's very simple to add different sensors to the same network and do a multidisciplinary science basically with the same infrastructure. But now let's go back to the project that I was working on and still working on. So basically, I said that in order to detect this cosmological signal, so to detect this 21 centimeter line in the frequencies between 100 and 200 megahertz, you don't only need to have a radio telescope which is sensitive to this emission, but you need to be really, really careful by analyzing the data. The problem is that the 21 centimeter signal, which originates from the epoch of ionization, is extremely, extremely faint. In the same frequency range, our own galaxy emits extremely bright synchrotron emission. We have many extragalactic radio sources which are also contaminating the signal, plus all of these signals are going through the ionosphere, which are scattering the radio emission in a similar way as the atmosphere is scattering optical light, and the reason why we see the stars to twinkle on the sky. And in addition to this, the telescope is placed in the area where people are living, so also there are radio frequency interferences coming from the Earth which can contaminate the signal. So the whole cosmological experiment was a big challenge, and there were many obstacles to study in order to be confident that we are able to detect the 21 centimeter signal. And my main research during my PhD was actually to model and to understand the galactic emission from our galaxy and extragalactic sources, and see how we can remove them from our data and find this faint cosmological signal. So unfortunately, during my PhD, the LOFAR telescope was not yet ready. So all my studies were theoretical, and I was really, really eager to continue this research, because after 4 years working on such a novel project, you are really curious and you really want to get a real data, to really get hands, so to say, dirty, and try to see what we really see with such a great instrument. So after I obtained my PhD at University of Groningen, I started my first postdoc at Astron. So I moved 60 kilometers more south from University of Groningen to the Dutch city of Dwingelo, to the Dutch Institute of Radio Astronomy. And after 2 years of postdoc there, I moved back for the second postdoc to Kaptein Astronomical Institute as a Venny Fellow, where basically I got a grant from a Dutch national foundation to develop my own and independent research. And during these years of a postdoc, basically the LOFAR telescope started to work, and we got some amazing discoveries. So we discovered that actually we are able, by detecting the radio emission which originates from our galaxy, so basically we have a fast-moving electrons produced in supernova explosions. They spiral around the magnetic field of our galaxy and emit this amazing radio emission, and this emission we can study with the LOFAR telescope. So on one hand, this emission is preventing us to see the faint cosmological signal, but on the other hand, this synchrotron emission of our galaxy provides us insight in amazing structures of plasma and the magnetic field in our galaxy, and this was really, really big surprise what fantastic images we can do with such instrument. And also the structures that we saw were a big surprise, because the current knowledge about the processes that were present in a galaxy could not explain such linear features and ordered structures that we observed. So of course I was eager to continue this research further, but also to develop my own research group which will tackle these problems. So in 2015, I got a permanent position at the Ruđer Bošković Institute in Zagreb, and I started to build my own research group. So now my whole perspective about the mobility and experience that I gained during my PhD years and postdoc years in the Netherlands, I tried to implement and develop further in Zagreb. So I started to apply both for a national and European funding, and finally I got both the national funding for my research project to employ a PhD students and postdocs, but also I wanted to internationalize my research group. And due to the differences between the salaries between the different countries and a certain competitiveness between different institutes, that was a kind of a big challenge to do it in Croatia. So despite the fact that I was doing excellent science and was involved in a great research, you need to somehow attract with some competitive grants or funding international researchers to join our team. And luckily we managed to do this with my current Marie Curie fellow, Andrea Bracco, where after 3 years of trying to apply for this Marie Curie fellowship, finally he got this fellowship and started to do excellent science now in Croatia, where basically we decided to understand all these structures that we observe in our galaxy through a multi-frequency analysis, and basically by looking the same part of the sky with a different eyes, so to say, to try and understand really what's there and how these structures can form and what's their origin. So at the end, I would like to stress out a certain benefits and challenges that I had during my career. So first of all, I think a great benefit of mobility in Europe, but in general in the world, is that actually for a young student who just finished or graduated at a certain university, gives him really opportunity to do state-of-the-art science, which is not necessarily developed enough in his home country. Secondly, if you are open to mobility, this allows in international networking and recognition, which I personally find it extremely beneficial for my further development of career. Because without a true international network, you are not able to develop further your independent research and to build your own research group. I also find it very beneficial that while working in the Netherlands and visiting some other institutes across Europe and the world, actually you are exposed to diverse working environments, and basically you can see the things, how the same thing can be done in a different way, or how work can be organized in a different way. And personally, I think this is a great benefit, because you can take the best from all different sites and try to implement this at the institute where you are currently working. And I think it's always best to try to test different environments and then try to find what suits you the best. Then, of course, going abroad from my own country to the Netherlands had a great impact for a further career development. Of course, if your network is good and if your research is great, then you will also get a broader career opportunities. And I already mentioned, I think especially for Croatia, it's extremely important that we have actions as Marie Curie, because through these actions or through ERC grants, you can really attract international researchers to come to Croatia or to some other countries and develop further and work further on development of excellence in that countries. From the point of view of the challenges, here personally I would say on the first level a balance between the private life and career development, which I think it's also very important in a research career, because we are all humans, and sometimes it's a real challenge to balance all of this. On one hand, you want to try different environments, You want to be open to mobility, but on the other hand, as the years are passing by, you also want to have a normal, let's say, private life, and then you are coming to 2-body, 3-body, or more body problems. Once when you have a partner or you have a kids, that mobility as such, it's not so easy. A different challenge, which I also had a few times, is that there are different national policies among different countries, and that in principle you as a researcher, you are not always aware of this. There are always some specific employment rules, taxes and things like this. And for example, once you move from one country to another country, it can happen that suddenly you need to face tax differences and things like this, which would be nice that these things, especially in research and mobility, are addressed in a better way. And finally, the last challenge, which I think needs to be addressed, and I would say that in the last couple of years, as I'm in Croatia, I see many positive and great already processes which are working towards this direction, but this is a bias during the peer review process, which we also personally experienced while we were applying for a Marie Curie Fellowship, where basically in the report, in the first and the second time, when we were just below the boundary of funding our process, for example, the project itself, all marks were great for the researcher, all the marks were great for the mentor, or the marks were great, but simply the environment at the Ruđer Bošković Institute did not get great marks because it was not as competitive as some other institutes. And then in the final call, we really tried to address that we don't see this as a negative thing for the project itself, but we really think this as a positive thing, because by only the pushing the boundaries and allowing people to do excellence, no matter where they are, if they are capable to do it, and if they will deliver an excellent science, personally, I don't think it should be an obstacle in the process. And I already know that there are certain mechanisms which are now trying to address this. So with this, I would like to finish, and thank you all for your attention.
Thank you very much, Dr. Jelić, for your fascinating keynote speech. You emphasized a lot of very interesting topics for our conference, actually. First of all, the fascinating nature of your research, I think, was very inspiring for many of us. I think what was most, maybe for the whole conference that we're going to have today, this idea that how you showed that mobility impacted your early career development. I mean, in fact, formed you as a researcher by moving to the Netherlands. But the interesting thing also for this conference is how you then returned to your country. So this idea of brain gain being very important at the systemic level, and also through your projects to allow incoming research from other countries to also contribute to the research environment at a system level here in Croatia. So that was a very important topic that we're also going to be addressing today. And you also obviously noted these issues of personal and professional growth, which is so important in mobility. I also noted with interest the issues that you brought up of these challenges about work-life balancing. I think we will come back to that in one of the panel sessions later today. Also issues of policies and how to make working environments easier for researchers to adapt to in different countries. And very interestingly, your last point about this challenge in the peer review process, and so this idea of allowing for pushing boundaries and not being too strict about saying, okay, you don't have the capacity to do this, and really trying to empower more research institutions to gain access to these competitive grants and projects. So thank you so much for opening so many of those questions.